Hi, everyone. Welcome back to Psych 3530. This is our last section of Factorial ANOVA. And what we're going to be working on in this lecture is interpreting factorial ANOVAs and the results from an ANOVA table. So let's just dive right into an example. Let's say that we want to test the effectiveness of a new drug. And we think that dosage of the drug and gender are both important factors in determining how effective this drug will be. And we think that maybe, in fact, gender and dosage will even interact. So, does the effectiveness, of a drug differ based upon its dosage and the gender of the patient? So, for this example, we're going to say alpha is 0.05. It's going to be a between subjects design, meaning we end up with four independent groups. We have males who have higher low dosage and females who have higher low dosage. Now, if we were to describe the nomenclature of this study, right, we would call this a 2 by 2 factorial design. And so we need a factorial ANOVA test statistic. We're going to sort of just wave our magic wand and have the computer do these stats for us, since we're not learning how to do it by hand. And so we can see our breakdown here under descriptive statistics of the means of our four groups, right? We have males with a low dose, males with a high dose, females with a low dose, females with a high dose. Now, this descriptive statistics table gives you the means, the standard deviations, and then how many data points, how many people essentially are in each group. So we can see we have 12 males in the low group, 12 males in the high group, 12 females in the low group, 12 females in the high group. We've got 48 participants. Now, this is also going to give us a male total and a female total, which is going to be helpful for interpreting that gender main effect. And then it gives us a total for just low versus high, right, independent of gender. And so if we have a main effect of dosage, then these numbers right here are going to be helpful in interpreting the main effect of dosage. Oh, here's some information that I apparently built into the little PowerPoint structure. So I'll leave it up for a second, so maybe you guys can take a look at it. But it's basically just what I've said. We've got two variables, each with two levels, for a total of 48 participants. And then we have some descriptive stats with our group means and the standard deviations. Okay, we've waved our magic wand, and the magic wand has done the factorial ANOVA for us. We're looking at the complete ANOVA table, the complete F table, where we want to focus on our three effects: the main effect of gender, the main effect of dosage, and the gender by dosage interaction. This table gives us the sum of squares for each of these effects, the degrees of freedom for each of these effects, the sum of squares divided by the degrees of freedom, which gives us our mean squared, and then each mean square, as we discussed at some point earlier in one of the sections, each mean square gets divided by the error mean square, or you'll often see this called the within subjects mean square. So we divide the effect mean square divided by the error or within subjects mean square to produce each F value, as we will see. So we're going to use all of this information, specifically the stuff highlighted in these boxes, in order to interpret our effects and figure out what's going on. So here is a big description of all the effects, just so you can see them. We're going to go ahead and just take them one by one. So let's look at gender. Gender has 1 degree of freedom because there were 2 levels of gender. So for your main effects, degrees of freedom is just number of levels minus 1. We took its sum of squares divided by 1, which gives us the same number again. And then we took this mean square and we divided by 2.494, the mean squared of error, to produce an F of 37.494. This is a very large F. our significance value is below our alpha of 0.05. And so we are significant. It appears that there is a significant difference in the effectiveness of the medication based upon one's gender. Now, we can't interpret the effect just yet because we need to go back and look at those group means from our means table. Let's move on to the next effect. We'll worry about interpreting later. The next effect is dosage, high versus low. Again, we see the same thing. Its sum of squares divided by its degrees of freedom gives us its mean squared. Its mean squared of 6.021 divided by the error mean squared produces an F of 2.414. This is quite a small F, and we can see that it is not significant. Its significance value is greater than our alpha. So what this tells us is that dosage, oddly enough, for a medication, doesn't seem to matter. The high versus the low dosage groups have the same effectiveness of the medication. But as we said last time, the sort of meat and potatoes of a factorial design is that we get this interaction, and that's really where the good stuff is. It's what we really want to highlight if we have an interaction, and we have one here. We took our sum of squares that the computer calculated for us. We divide by degrees of freedom. The degrees of freedom for your interaction term is just the product of your main effect degrees of freedom. So it's this degrees of freedom times this degrees of freedom gives us this one. So 1 times 1 is 1. So we would take the gender degrees of freedom times the dosage degrees of freedom. It's easy to remember because it literally has this little sort of multiplication star symbol, right? Gender times dosage or by dosage. So we divide by 1, and then we divide by 2.494, right? These two mean squares to give us 15.443, another rather large F with a very small significance value. It's below alpha. This is a substantial, large, and statistically significant effect below our alpha of 0.05. So this tells us that there is, in fact, an interaction between gender and dosage. Again, we can't interpret it quite yet. We need to go back and look at the means tables as well as probably a line graph to help us interpret this interaction. Now, we also need to work on finding a critical value in an ANOVA table, and we're going to go ahead and find it for each of our effects, and then show that these effects that came out as significant are significant because their Fs are above this critical value that we're going to find on the table. So we have 3 critical values that we need to look up, right? We need to look up the critical value for the effective gender, the effective dosage, and then for the interaction. Now, in this example, the critical value is going to be the same for each of them because they have the same degrees of freedom. That does not necessarily have to be the case. If dosage had 3 levels or 4 levels, then it would have 2 or 3 degrees of freedom and would thus have a different critical value than gender. And then we would multiply gender and dosage together to get a degrees of freedom for the interaction that might also differ. But when we translate these degrees of freedom into this table over here, this critical value table, we use the effect degrees of freedom as the numerator degrees of freedom along the top because it's in the effect mean square is in the numerator of the formula for our F value. And we use the error degrees of freedom, 44 in this case, as the denominator degrees of freedom down our left axis because the error mean squared of 2.494 is the denominator of our F value calculations. So we're going to take a 1 for each effect and use that as our numerator degrees of freedom. And then we're going to use 44 as our denominator degrees of freedom. We only have to do this once because all 3 effects have the same degrees of freedom, but we'll see an example later on when that's not the case. Now, something that's a little problematic here is that 44 is not on our critical value table. We jump from 40 to 60. Basically, the table does this because if you look at the small difference between these numbers, right, the table is basically saying that the difference between 40 and 41 is pretty negligible. The difference between 40 and 42 is pretty negligible. And so we can just jump these sort of big chunks of degrees of freedom without really costing us much in the way of specificity with our critical value table, right? 4.0847 is very similar to 4.0012. So what do we do if 44 isn't on the table? Well, we just move up the table until we hit the next number, which would be 40. If our degrees of freedom was 38, right? Notice 38 is not on the table either. We would move up to 30 and use the degrees of freedom for 30. We move up the table because moving up the table gives us a more conservative test. The critical values get larger as we move up the table. So moving up the table makes it harder on ourselves. And we always want to be more conservative. So we move up the table, not down the table when our degrees of freedom is not present. So we're going to be actually, instead of 44, we'll be using the row of 40 and the column of 1 to give us a critical value for all three of our effects, both main effects and the interaction, of 4.0847. Again, all of these critical values, all three critical values are the same because all three effects had the same number of degrees of freedom. If the effects differed in their number of degrees of freedom, then they would differ in their critical value. Okay, so we can bring this critical value back for interpretation. Remember, it was 4.0847. And notice that our significant main effect of gender is significant because its F value is greater than 4.08. So we would reject the null because our F value is bigger than our critical value. The computer already tells us that by telling us that it's a very, very small p-value. But we reject the null. We conclude that gender does have a significant effect. We can go to our means table. We can look up the total for all males and see that the medicine scores a 5.83 on effectiveness for males, but the medicine only scores a 3.0417 for effectiveness in females. So we know from the ANOVA that this effect is significant. We can see from our means table that men outscore women on the effectiveness of the medication. So we conclude that the medication is more effective for males than it is for females. Boom. Main effect interpreted. However, next we need to interpret our gender by dosage interaction. We could do that by looking at the means tables here. It's just kind of broken down to be a little more clean. Right? We have our low males, our high males, our low females, our high females. But again, interpreting interaction effects from a means table is quite difficult. We prefer to just look at the figure. So here it is. We have low dose on the left of the x-axis, high dose on the right of the x-axis. We have effectiveness on our y-axis, and then males are our blue line and females are our green line. So what we can see is that we have what we might call a spreading interaction, right? When dosage is low, males and females look fairly similar to each other, right? Males are still a little higher. Remember, we had that main effect of males being, of the medicine being more effective for males than females. Males are a little higher, but they're not far away from each other, right? They're fairly close. But then as we move to a high dosage of the medication, males and females diverge wildly, right? The medicine gets more effective for men at a high dosage and actually gets less effective for women at a high dosage. So we have this spreading effect, which is causing our slopes to differ dramatically, right? Our rule of thumb, if the slopes differ, then you probably have an interaction. And so we would say that, well, what is the effect of dosage on drug effectiveness? Well, it depends upon your gender, right? That's our famous term for interactions. It depends upon. How effective is a low dosage, or how effective is the medication? Well, it depends upon the interaction between dosage and gender. Now, remember that we had a main effect of gender, but then we also had this interaction. And in our interpretation, we would want to include both, but we would really want to play up this interaction. This is the good stuff. This is what actually is going on. And in fact, if you're a medical professional, this tells you that you want to give males a high dose, right? It's most effective for them at a high dose, but you would want to give females the low dose because it's more effective for them at a low dose. The males and females have the opposite pattern here. So this is this interaction in this case is really dramatic, is really important, and in a medical sense, could have some dire health consequences for both males and females. So getting this interpretation correct is really important. So we can see again that the effective dosage depends upon gender. Okay, so what we want to do next is practice sort of understanding where these F values come from within an ANOVA table. And so we're going to do that with an example that doesn't have any context, right? We're gonna start with an example that doesn't have context, and then we're gonna add context and attempt to calculate and interpret our F values. So here we have some made up data. We don't even really have defined variables, right? We just have the effect of variable 1, the effect of variable 2, and the interaction of variables 1 and 2. Just like in the computer output, we have our sum of squares for each of those effects. We have our degrees of freedom for each of those effects. And we have a mean squared for each of those effects, along with our error, or what again here can also be called within treatments mean squared. Notice how we do get some variability here in degrees of freedom in this example. And so what that tells us already is that variable 1 had 2 levels, right? Because its degrees of freedom is levels minus 1. Variable 2 had 3 levels because its degrees of freedom is 2. So 3 minus 1 would be 2. So it had 3 levels. And then the interaction degrees of freedom is the product of the main effect degrees of freedom. So 1 times 2 is 2. So we'll need to end up looking up, once we go to try and make decisions about significance, we'll end up looking up 2 different critical values. One critical value for variable 1, and then actually a different critical value for main effect of variable 2 and the interaction. But first, I want us to answer these 3 questions. We're going to learn how to calculate our F from these mean squared. We're going to practice, again, finding critical values and then determining which effects are significant. So let's calculate those F values. We're working with our mean squared. We take each mean squared of each effect. So for variable 1, its mean squared is 120. And we divide by the within treatment's mean squared of 8. So 120 divided by 8 gives us an F value of 15. In variable 2, we take the mean squared of 130. We divide by 8 to give us an F value of 16.25. And for the interaction effect, we take the mean squared of 10, we divide by 8 to give us an F value of 1.25. So it looks like we're probably going to have a main effect of each of our variables. Those are pretty large Fs. And we're not looking too hot on our interaction here. That's a relatively small F. Also notice how the mean squared of the main effect of variable 2 and the interaction, its sum of squares gets divided by 2 to produce its mean squared, right? In our last example, they were all 1, and so the sum of squares was the mean squared. That is the case for variable 1 because it has 1 degree of freedom, so its sum of squares just becomes its mean squared. But variable 2 and the interaction are divided by 2 degrees of freedom to produce their mean squared. But what we really need to worry about is knowing how to take each of these mean squares and just simply divide by the within or error term to get the F value. So these are our 3 F values. This is what's going to tell us whether the effect is significant or not once we compare it to the critical values. So let's look at our critical value for variable 1. First we need to remember to bring with us this degrees of freedom within, right? So we want to bring with us all of these degrees of freedom, 1 for each effect, so 1, 2, 2, and then they will all collectively use the within degrees of freedom of 24 for their row degrees of freedom. Okay, so first up is variable 1. Variable 1 had 1 degree of freedom. The within or error degrees of freedom, that is the quote-unquote denominator degrees of freedom, was 24. So we're working in the 1 column. We're working in the 24 row to give us a critical value of 4.2597. We want to sort of write that down and remember it. Then variable 2 had 2 degrees of freedom in the numerator. So we actually bounce over to this 2 column. It had the same, obviously, 24 denominator degrees of freedom. They always will. And so we just move over 1 column, and now we have a smaller critical value of 3.4028 for variable 2. And then this stays the same for the interaction because the interaction also had 2 numerator degrees of freedom. So its critical value is also 3.4028. Okay, so now we want to compare our F values that we calculated previously to our critical values that we just established from the table. So remember, if the F value is larger than the critical value, we reject the null, and the effect is significant. If the F value is smaller than the critical value, we fail to reject the null, and the effect is not significant. So we take variable 1. Variable 1 has an F of 15. It has a critical value of 4.25. So this F value is much larger than the critical value. The effect is significant. Something is happening with variable 1. We have a significant main effect. We do the same thing for variable 2. It has a large F of 16.25. We compare that to its critical value. Oh, sorry, that should say 2. My bad. We compare it to the critical value of variable 2, which is 3.4028. So its F is larger than this critical value. So we have a significant main effect of variable 2. And lastly, looks like we do not have a significant interaction because the interaction has a small F of 1.25, which is less than its critical value of 3.4. So we do not have a significant interaction. So in this example, whatever it is, right, it's without context. We're just working on the process here. Whatever it is, we know that there's no interaction, but each of the variables has its own independent effect on the outcome. Okay. Let's do an example with some context. Let's imagine that our research question is we want to know the impact of diet and frequency of training on the maximum bench press weight for various powerlifters. What is the impact of diet and training on the maximum bench press weight for powerlifters? We're going to assume an alpha of 0.01. And I want you to answer the following questions. What is the F value for each effect? What is the critical F value for each effect? Which of the effects are significant? And then how should we interpret these significant effects? Let me draw your attention to these tables over on the right. On the top in blue, we have our means table. You can see that the variable diet is up on top. We have vegetarian powerlifters. They actually do exist, oddly enough. We have carnivorous powerlifters who only eat meat. And then we have some omnivore powerlifters who eat both vegetables and meat. Our powerlifters train either 2 times a week, 3 times a week, or 4 times a week, training down here, the other variable on the left. And so we actually end up with 9 separate groups of powerlifters because we have a 3 by 3 factorial ANOVA. And we can see their bench press maxes here in the middle of our table with our numbers. So this is our means table. It shows us the exact mean of each of our 9 groups of powerlifters. And then down here is the ANOVA table with our sources of variability, the main effect of diet versus the main effect of training frequency versus the interaction of diet and training. We have our sums of squares. We can see that we have 2 degrees of freedom of diet because 3 minus 1 is 2. We have 2 degrees of freedom of training because 3 minus 1 is 2. And we have 4 degrees of freedom for the interaction because 2 times 2 is 4. And our mean squared for the effects and our mean squared within. So what I want you to do is hit pause, and I want you to answer these 4 questions to the best of your abilities. Calculate each F value. Go look up the critical F value for each effect. There's actually a critical value table on the next slide. So if you have the static PowerPoint, not the video of the PowerPoint, but just the static PowerPoint slide, go ahead and click to the next page. It's right here. And you can have a chance to look up the critical F value for each effect using these degrees of freedom. Then I want you to determine which of the effects are significant. And then I want you to try and interpret. You're going to have to come back and look at these means tables, or the means in the means table, in order to try and interpret whichever of these effects is significant. So hit pause. If you have to go back and look at our previous 2 examples to sort of help scaffold you on this, that's perfectly fine. Just, write down all these numbers over here in these tables, maybe on a piece of paper. Just write them down. And then if you have to go back and look at the steps in the previous examples, that's perfectly fine. Take a few minutes and try and answer these 4 questions, and then hit play on the video when you're ready to check your answers. So go ahead. Okay, hopefully you're back after having tried to answer these 4 questions. And let's just dive right into it. What is the F value for each effect? Well, we take our mean squares and we divide each effect mean squared by the within or the error mean squared. So for diet, 6 divided by 5 is 1.2. Not looking good for diet. For training, 64 divided by 5 is 12.80. And for the diet by training interaction, we take the mean squared of 27.5, we divide by 5, and we get an F value of 5.50. Those are our 3 F values. We can go ahead and just kind of slide them on over there, and they'll stick with us for the rest of the time. So we have our F values. Now we need to know which of these F values is significant. So hopefully you took some time to work with that critical value table. Here's what you should have done. You should have identified the critical value for diet, right? It has a degree of freedom of 2 and 16. So 2 and 16. The main effect of training has the same critical value because degrees of freedom 2 and 16, right? So it is also 6.2262. And then the critical value for the interaction term, 4 degrees of freedom. So we have to bump over here to our 4th column, and we stick with 16 within degrees of freedom to give us a critical value for the interaction of 4.7726. So now we need to compare our observed or calculated F values, which we see over here on the left, the F for diet, the F for training, the F for the interaction. We need to compare these numbers to those 3 critical values that we just found. So clearly diet is not significant. Right? Apparently it doesn't matter what diet a powerlifter is on for their bench press. Obviously I made up these numbers. Now we do have a significant effect of training frequency. So that means we're going to need to start, we're going to need at some point to interpret our training frequency numbers over here. So because its F value of 12.8 is larger than its critical value. And we also have an interaction, which is a little scary considering we have a 3 by 3 factorial ANOVA, but we got to try and interpret this guy because the F value is larger than the critical value. So let's dive into the effect of training. If we look at how bench press varies with frequency of training, we can see that training more increases our bench press weight, specifically at the distinction between 3 times and 4 times per week. It doesn't look like there's much of a difference between 2 and 3 times per week, right? 44 to 455, 440 to 445, 445 to 440. There's not much difference going on there. But then when we add this 4 times per week condition, we see these big gains in bench press weight. So what this tells us is that frequency of training matters. We knew that from the main effect, but it tells us that training more increases bench press capacity, specifically when you train 4 times per week. Now let's move on to interpreting our interaction. There's one critical value here. I probably shouldn't say critical value. There's one important or maybe crucial value over here. It's the omnivores that work out 4 times per week. We can see that they have basically superhuman strength. I don't know what the world record is for bench press, but it's probably somewhere around 680. That's insanity. So we see that the omnivores that work out 4 times per week have a much larger bench press than everyone else. Something funny is going on about the combination of omnivore by training, right? And so it looks like training more times per week is particularly beneficial for omnivores, right? They make dramatic gains when they go from training 2 or 3 times per week to 4 times per week. Everybody makes gains when they move from 3 to 4 times per week, but omnivores, for whatever reason, are particularly able to take advantage of that extra training, and their bench press max balloons. Now, of course, this is much easier to do or to interpret in a figure. So what I want you to do is pause again, and I want you to graph out this means table. I want you to put the number of trainings per week along the x-axis, and I want you to put our diets as different colored lines or different types of lines. And then I want you to plot all 9 of these values and then see if you can interpret the interaction then. Because it's what I just did is very difficult to do, to sort of eyeball and figure out which numbers are really important for the interaction. And in fact, I've sort of intentionally made this one obvious. 680 is, this huge departure from the rest of the numbers, and that's not always going to be the case. So we want to make sure that we can visualize this effect as well. So go ahead, press pause, and build that chart, and then we'll come back and we'll look at it together. So remember, put training on the x-axis, and then put diet as 3 different types of lines in your line graph. So go ahead and hit pause. And we're back. And my next slide has such a graph. This is not strictly APA style for graphs, but I did it this way so that we can sort of visualize it better. Oops, my bad. I told you to put the wrong thing on the wrong axis. I told you to put times of training on the x-axis, when in fact what I did was put diet on the x-axis. I'm not going to go back and re-record this whole 30 or so minute video because of that mistake. Just go ahead and maybe draw out this graph as well. I'll give you some practice with drawing out graphs. So draw out a graph that puts diet on the x-axis, and then a graph that uses training frequency as the lines. You can also maybe take the opportunity to look at my graph and look at your graph and notice that they should convey the same information. The lines will not be the same because we put one variable on the lines and the other on the x-axis from each other, but it should convey the same information, and the interaction should be obvious as well. So remember, in an interaction, what we're looking for is a change in slope, and we can see one pretty dramatically for our 4 times trainers, but only when they're in the omnivore condition, right? All the slopes are basically the same everywhere else around this effect, right? All the slopes are the same except for the slope created by these omnivores, right? This is a dramatic interaction. So what this tells us is that the effect of diet depends upon frequency of training. We can see the main effect of 4 times training per week, right? That sort of yellowy gold line is higher than the other 2 lines. That's our main effect that we observed, right? That 4 times of training per week means you bench press more. But it is a dramatic difference only for the omnivores, right? So being an omnivore plus training 4 times a week gives you this dramatic difference. So again, we could put this in the other direction with the other variable. We could say, what is the effect of training frequency on bench press maximum? Right? What is the effect of training frequency on bench press maximum? Well, it depends upon your diet. For vegetarian and carnivore diets, it doesn't matter, right? There is no effect of training frequency. But for omnivores, training 4 times per week provides this huge dramatic difference, right? The fact that these vegetarians and carnivores get a small boost from training 4 times per week is interesting, but it's not nearly as interesting and important as this interaction effect of our omnivores that we would want to highlight. So that's it for interpreting and using ANOVA tables and a factorial ANOVA. Sorry for my little flub about the graph, but you got some extra practice with either building graphs or seeing that the same information can be conveyed in different ways by putting different variables on the x-axis versus the lines. Doesn't matter. It's the same information being displayed. So thanks, everybody. This concludes Factorial ANOVA. You have a study guide for the exam on iCollege, as well as some practice problems, a practice worksheet with the answers to that worksheet uploaded on iCollege. So as you're preparing for this exam, go back through, do these examples from all the different lectures, from all the different videos, as well as take advantage of that study guide and the worksheet that's on iCollege. Thanks, everybody. Have a good one, and good luck on the Factorial ANOVA and Factorial Design exam.